So let's take a look at another example problem. This is the first example of spectra using data for nuclear magnetic resonance. So as usual, we should really start with the infrared spectroscopy first. And as we look for these main peaks, we've got a very strong broad peak above 3000 at about 3300, and that's usually the range for a carbon to hydrogen stretch when we're dealing with an alkyne. And sure enough, we look at about 2200, we see that peak for the carbon to carbon triple bond stretch itself, and then down at about 600, that incredibly broad peak, which should be the bending vibration for the carbon to hydrogen bond again, coming off the alkyne bond. So it definitely looks like we have an alkyne. All the pieces are there. If we look at the mass spectroscopy, now our molecular ion peak up here, of course, is at 68 grams. So there doesn't seem to be anything other than carbon and hydrogen in the molecule. So we can just simply divide by 14, and that works out into 14 just over 4 times, so we get C4H8 and 12 units of mass to account for after that, which very nicely gives us an extra carbon. So the actual chemical formula looks like C5H8. Of course, if the molecule was saturated with 5 carbons, that's CnH2n plus 2 rule, that would suggest 12 hydrogens when completely saturated. So we're down by 4 to get to the 8, which agrees with the alkyne structure. There are 2 pi bonds being suggested from this mass spectroscopy. So now that we're pretty sure it's an alkyne, let's look at the nuclear magnetic resonance and look at those peaks. Now a peak furthest to the left, the most de-shielded, downfield, is a peak at about 2.7. And that's definitely slap in the middle of the range that we expect for the hydrogen on the alkyne triple bond. It's a singlet, as we expect, with no nearby non-equivalent hydrogens. And then next door to that we have a triplet, and that's almost as strongly de-shielded at about 1.9. So we're looking at hydrogens on a carbon on the other side of the carbon to carbon triple bond, so the 2 hydrogens there, and because the signal is split into a triplet, they have 2 non-equivalent neighbours, the n+1 rule. If we switch to the peak furthest to the right, the furthest upfield and the most shielded, it looks like it's a terminal methyl group again. So it's 3 hydrogens on the other side of the molecule from the alkyne bond, and again, being a triplet, it has 2 non-equivalent neighbours. Now remember, we've got 5 carbons in all in the molecule. 1, 2, 3, 4. So we're only looking for 1 more carbon. Of course, the methyl group at the end, it has 2 non-equivalent neighbours. And this group next to the alkyne bond, it also has 2 non-equivalent neighbours. So the 2 hydrogens here must be the missing link in the middle. And that explains why it's such a nasty multiplet. The 3 hydrogens at the end from this peak here, of course, trying to split the signal for these 2 into a quartet. But for each of those 4 peaks from the quartet, there's 2 hydrogens on the other side, 2 hydrogens here, which are trying to split each of those signals into a triplet. So this is why we get this big ugly mess of a multiplet for these 2 hydrogens. So that explains our entire molecule, which we can show like this. So 1 hydrogen at 2.7, and then 2 hydrogens at the 1.9, then another 2 as a messy multiplet at 1.5, it looks like, and then of course that terminal one methyl group at 0.9.